was reading the bios on the speakers for this session, I was reading that we were going to have 2 speakers who were going to talk about the tallest to-be building in Europe. The only problem being is that they were going to talk about a different building, but I think you read those bios as well. The thing, of course, is that it may sound a bit silly, but it's not really all about height. That's one thing that this conference is learning, is that there's so much more about tall buildings than just the height, which I think makes it very interesting. All right, on to Moscow. Moscow, of course, is a city whose skyline was dominated for many years by 7 sister buildings, excuse me, that until recently would be enjoyed by many new buildings that are really embodying the rapid change and the rapid growth of Russia nowadays. Today, talk to us about that is Mr. Bob Halvorson of Halvorson and Partners. He will be discussing the Russia Tower.
This is partly about the Moscow Tower, and it's also partly the story about a collaboration over the last 10 years between our office and that of Halvorson and Partners. In working on the series of buildings you'll see culminating in the Moscow Tower, we tried to incorporate the ideas of efficiency in tall building design, some fundamental ideas that we've had about that. And I think as we go through this, the sort of interesting thing that you'll see is that each of these buildings has a very unique form, a very unique shape, dependent on the site, the owner's program requirements, the owner's preferences, certainly, but all carry through these fundamental ideas of efficiency that we've developed. Now, why are these principles important? Well, obviously, in a tall building, the structure forms a major part of the cost. It certainly sets the speed of construction. So it's a fundamental part of the feasibility of a tall tower. The collaboration is important. As we heard yesterday, there were 40 consultants, I think, on the Burj Dubai. So each of these projects really has to be a collaboration so that the expertise of all these different people and companies can be reflected in the final design. So, now to these sort of fundamental principles that I talked about. They're very simple. And I think if, with a good understanding of these, anybody could probably design a tall building. But the first is that in designing the building, it's desirable to spread the gravity loads out as far as possible at the base of the building to help in resisting overturning forces. Well, sorry, I thought this might get a chuckle, but the second idea is to carry wind overturning forces on the same elements that are carrying gravity loads. And as you can see, the taller that you get, the broader the base you need. And if we think of these tall buildings as cantilevers from the ground, the first 2 principles have established the flanges of this beam. Excuse me. And then the third idea is that those flanges need to be linked together with some kind of a rigid web, just like the web of a steel beam. And then the last idea is that is to try and resist the lateral forces on the building through members loaded in an axial sense rather than in bending. And even better yet, an axial compression rather than tension. Because in concrete elements, obviously concrete's very good in compression, but we have to reinforce it if there are large tensions. In the steel building, the steel itself is very good in tension, but if there are significant tensions, the connections need to be designed for it, and the connections become expensive. Now, looking at about a half a dozen buildings that we've done over the years, some concepts, some competitions, some real buildings, with Halvorson and Partners. This was the first, started in 1999 in Chicago, a corporate office building. It never went ahead, it stopped on September 11th. But the scheme we developed was a diagrid system where all the gravity loads in the building were supported on sloped columns, and these sloped columns also resisted the lateral loads on the building. So how does it stack up against our principles that we established? Well, here we're using the entire building width to resist overturning forces. In fact, at the base, you can see the columns flare out to create an even wider base. All the gravity load and the wind load are carried on the same elements. Second principle. The linkage through the building between the flanges of the beam, if you will, are these diagonals, which are very rigid. So, and all the lateral loads are resisted as axial loads and members. There's no bending in any of these members created by the lateral loads. So conceptually, it's very efficient. And there's sort of a fifth principle at work as well. And that is, if you look at the cost of a piece of steel to carry a compression load over a given distance versus the cost of a piece of concrete to carry that same load. And you can put in your own material strengths and local costs in the countries that you're from. But generally, the concrete is perhaps 1/5, 1/6, 1/7 the cost of steel in carrying those loads. And it also has other advantages for tall buildings in dealing with wind loads. It has additional mass, which helps in accelerations. It generally has additional damping, which helps in accelerations. And it's inherently monolithic. In other words, each piece of concrete is connected one to another just through the construction process. Whereas in a steel building, these pieces need to be connected together. So in this building, even the columns we were looking at as composite steel tubes filled with concrete. A slightly later example, competition entry for the Milan Fair site. In this building is a residential building, and there are 3 units per floor located in these, they're really called pedals or pods, I'm not sure which. In the center there was an atrium space for vertical circulation. The atrium was floored over every 6 floors with a park, and so the central area was sort of a public park and for vertical circulation. Thank you. And our idea for this was to locate reinforced concrete walls within, hidden in the walls within each of these pedals, and then link those together, well, the blue bits in the elevation that you see, and then link those together with the structural steel diagonals, the red diagonals that you see in the elevation. So here, again, we're using a large dimension of the building, not all the way out to the tips, but certainly a large dimension of the building. We're linking those together rigidly with the diagonals, so we have a rigid web. We're carrying both gravity and wind loads on the vertical elements. And again, there's no bending in any of the members created by lateral loads. It's all resisted by axial forces in those members. Another building in Madrid that's just about completed, designed originally for Repsol, a Spanish oil company, bought recently by a bank in Madrid. In this building, an office building, there are 2 cores, the orange bits you see there, that extend the full height of the building. And these cores carry all the gravity load in the building as a total, and resist all the lateral loads. Spanning between those 2 cores is a structural steel, actually 3 structural steel bridges. There's 3 segments over the height of the building. And within each of those segments, there's a 2-story steel truss at the bottom of that segment, spanning from core to core. And that truss serves to take the loads from the local steel columns in each segment and transfer them to the concrete cores, which is where we really want it, in the cores that are resisting lateral load. So here again, let's compare this to our principles. In the long direction, in the direction of the 2 cores, obviously the gravity load is spread out even wider than the building itself. In the other direction, where the cores alone resist the wind load, they're fairly narrow. It's only the cores are only 19 or 20 meters deep for a 250 meter tall building. So we have like a 12.5 to 1 slenderness ratio. But because all the gravity load is on these 2 cores, squashing them down, even at that slenderness ratio, we don't get uplifts and tensions in the walls. Some of you may have seen this on the tour yesterday, the Index building in Dubai. This is a mixed-use building with office in the base, residential in the top part. And the lateral system, you can see in the schematic there, in the short direction building is sort of 4 fin walls that pass through the building. And these taper outwards towards the bottom of the building to expand the base, if you will. And then in the long direction, we have the 2 cores on either end of the building, which actually are linked together at mid-height by a transfer curve and at the top. So in the long direction, we sort of have a 1-bay frame with 2 beam levels, if you will. Here, in the office floors, in the bottom of the building, we have a 27-meter clear span, which you wouldn't think of as efficient, but by using composite steel floor trusses, much like the Sears Tower uses, we're able to deliver the gravity load directly to these reinforced concrete elements, which carry it down to the foundations. And again, the concrete is a relatively cheap way to carry these loads. So, in a lot of ways, this also follows these fundamental principles about efficiency that we've talked about. The gravity loads are spread out in the short direction as far as we can, given the narrow nature of the building. And in the long direction, while this sort of 1-bay frame is not particularly rigid, it's adequate for the building. Another project that's currently under construction in Abu Dhabi, Central Market Project. There are 3 towers, the tallest of which is shown here. It's 88 stories, a residential building. And in this building, we've utilized a core and outrigger system, which has come up over the last 20 years or so. And the core of this building is the yellow arrangement of concrete walls in the center of the plan. There are columns around the perimeter, the blue elements. Here the columns are really more like walls, in that they're being hidden in the walls between the rooms of the units. And then at 3 locations over the height, top, middle, and bottom, we have outriggers, effectively story height concrete walls that go from the core to the exterior to try and engage the entire building in resisting lateral wind loads. So again, here we've used the entire building dimension to resist wind loads, which is necessary because this building is, I think, about 11.5 to 1 slenderness ratio. So it's a very, very slender building. The overturning forces are resisted as axial forces in the perimeter columns, which is good. We're carrying gravity loads on concrete, which is good. And the outriggers are a fairly rigid link, a fairly rigid web in our beam, if you will. Adequate for the purpose, but not entirely rigid because the owner is interested in having flexibility on those floors without the outriggers. And lastly, the Russia Tower in Moscow, which is 118 stories, 600 meters tall, mixed-use building, office at the base, hotel in the middle, residential on the top floors. Again, somehow I have the wrong presentation here, so I'll skip through a couple of those. But when the developer walked in, he had a program. Again, he wanted office, hotel, and residential. He had 3 different investors, each of whom was interested in one of those. So the developer envisioned 3 buildings on his triangular site. But as Halvorson and Partners studied this, the 3 buildings really are very close together. A large portion of their perimeter would be, staring at their neighbor buildings. So after a while, excuse me, the forms evolved where these 3 buildings were more narrow rectangular buildings oriented like blades of a fan, so that there were open views and light and air accessible to the facades. Same idea as the Lake Point Tower project that Adrian described, or the reasoning behind the Burj Dubai. And then as the design evolved further, these 3 buildings we spent a lot of time thinking about linking these buildings together, because individually they were all very tall, very slender, and would not therefore be particularly efficient. So we took the approach of trying to link these three buildings together at their inner edge, which is indicated in these diagrams. And then because of the program, like we've just heard, the office floors at the base required a bigger floor, hotel, medium, residential, small. So the tapering became a part of the project. And again, we felt it would also assist us in terms of both reducing wind loads as well as reducing this vortex shedding issue. The developer, however, was still interested in organizing uses, like are shown in the left-hand part of the slide there, where each use had its own wing. Now this makes cores not very efficient and things like that. And when he asked us whether these three wings could be phased, we explained that was sort of like building two legs of a tripod. The idea went away, and we wound up with a more conventional organization on the right-hand side. In thinking about structural organizations of how to achieve a building like this, really there are only two ideas. I might add, these are the sketches, hand-drawn sketches that we did at the time. There are really only two organizations that I can think of. The one on the top there says maybe it's a bundle tube. Maybe the central core area is a tube, and then each wing is a tube. And these tubes are hooked together, much like the Sears Tower. Or another alternate approach might be, we have a spine in the building, a central core, and then the faces of the wings, there's some sort of rigid plane there that serves to brace this central spine. And here, it's really much the same idea as Burj Dubai. Here, the developer wanted clear span lease spaces on the office floors. So we were trying to eliminate any interior columns in the office floors. So the only way we could form these sort of braces was not internal, like Burj Dubai, but along the face of the building. So we looked at some ideas. This is one where there is a central core, and perhaps there's some bracing that extends out along the wings in a tapered fashion, reflecting the wind forces in the building. We looked at other ideas where perhaps there's a central core and outriggers engaging other columns out in the wings. But we only started to get excited when we started thinking about structural organizations in the wings that related to the geometry, that related to the slope at the ends of the tips. This is one where we developed a diagrid, where the angles of the diagrid match the slope of the tip of the wing and the slope of the underside of one of the wings. And this was a nice scheme. We modeled it, and it was stiff and good. Project architect Michael Gens had just finished the Swiss rebuilding, and I think he was tired of looking at diagrids, so this went away sort of quickly. But then this was an idea that we had, again, where there's this central spine in the building, but instead of having vertical columns in the wings, why not slope them all parallel to the slope at the end of the wing? The thinking was that this is, these slope columns could brace the center core. And we had ideas that with parallel wings, the bays would be typical. They'd be offset on each floor, but typical nonetheless to facilitate construction. Well, I tended to do these sketches late at night after the family went to bed, so I sent off that last sketch probably at midnight or 1 in the morning. When I came in the morning, the sketch on the left was on my desk, where Michael said, "Gee, Bob, that was a very interesting idea, but can you do it this way, where the columns radiate from a point out at the end of the wings?" So it was a completely different idea. Did away with the repetition, but on the other hand, conceptually, it does bring all the gravity load out as far as possible on the site. With just those radial columns that you see on the right here, though, we did an analysis, and the building, while very stiff laterally, had a torsional period of 12, 13 seconds. In other words, probably too long. So we came up with the idea of putting in what came to be known as reverse fan columns. The fan columns are the principal columns that slope upwards to the core, and then the reverse fan columns sort of metaphorically bounce off the core at the same angle that they hit it. And so these show those two options. And after a period of time, I think everybody came to really like the sort of double layer bracing, being more organic and more complex. So that's a very short introduction to the project. And I think, you know, from my standpoint, I very much enjoyed these collaborations because each one was unique. It depended, each of these buildings depended on their site, their program, the owner's desires, but this idea of efficient structural concepts lead through all these projects. Thank you.